Welcome to The Explainer. Today, we're digging into a really huge idea from DeepMind that pretty much turned the world of AI development completely on its head. So I want you to imagine two AI models. Over on the left, you've got Gopher, a real titan of a model with a brain built from 280 billion different components, or what we call parameters. And on the right, that's Chinchilla, a model that's just a quarter of the size, with only 70 billion parameters. All right, so which one do you think is smarter? You're probably thinking the bigger one, right? Well, the answer is not what you'd expect, and it actually reveals this powerful secret about how to build the absolute best AI, especially when you're working with a fixed budget. To really get why this question is so important, we gotta rewind the clock just a few years. Back then, the thinking in AI was pretty simple. Bigger is always better. That was the rule. And you can see this AI arms race right here on this slide. Just look at the model sizes. They just kept ballooning. From GPT-3 at 175 billion parameters to Megatron Turing's absolutely staggering 530 billion. But, and this is the key part, look at the training data. For all that massive growth in size, the amount of data they were actually learning from, it barely moved. Well, this led the researchers at DeepMind to a pretty stunning conclusion, and they said it perfectly in their paper. Current large language models are significantly undertrained. They were basically building these massive, powerful engines, but then only giving them a tiny thimbleful of fuel. It's like having a bodybuilder with incredible muscles who, just never went to school. And that realization, it sparked this fundamental question that challenged the entire recipe that everyone was using to create intelligent AI. I mean, if just making the models bigger and bigger wasn't the whole story, then what was everyone missing? Okay, so to really understand this recipe, let's just quickly define our ingredients. The first one is parameters. The easiest way to think about these is just the raw size of the AI's brain. So more parameters means a bigger brain, which gives it more capacity to learn really complex stuff. And our second ingredient is training tokens. These are basically just pieces of text. So if parameters are the brain's size, the tokens are its education. The more tokens it gets to see, the more it learns about language and facts and how to reason. Now, that old recipe was all about the size. The thinking was, if you had 10 times more computing power, you should make the model's brain about 5.5 times bigger, but you'd barely increase the data it learned from. You can see that imbalance right here. It's all brain with very little education. So the DeepMind team set out to find the truly best recipe. Given a fixed amount of computing power, what the researchers call a compute budget, what is the perfect balance between the size of the brain and the amount of education? And they didn't just take a guess. Nope. They ran this massive experiment. They meticulously trained over 400 different language models, playing with everything from the parameter counts from 70 million all the way up to 16 billion. And feeding them all kinds of different amounts of data. By putting all the results on a graph, plotting the performance of all 400 of those models against how much it cost to train them, they could finally see the hidden pattern. And that allowed them to figure out a new, much more efficient rule for building AI. And here it is. This is their groundbreaking finding. They discovered that for the best results, that old imbalanced recipe was just wrong. Turns out, you should scale the model's size and its training data in equal proportion. For every dollar you spend making the brain bigger, you should spend another dollar on its education. Simple as that. But of course, this wasn't just some theory they cooked up. They put their new rule to the test. They built a brand new model from the ground up, designed to be perfectly balanced, what they call compute optimal. So let's meet the challenger, Chinchilla. Like we said, it's 4 times smaller than the giant Gopher model. But, and this is amazing, it was trained on 1.4 trillion tokens of data. That's over 4 times more data than Gopher saw. And here is the absolutely crucial part. Both of these models were built using the exact same amount of computational energy. So what happened when these two went head-to-head? Well, in what you can only describe as a stunning upset, the smaller but much better educated model, Chinchilla, just completely dominated its larger, undertrained rival
across a whole massive range of tasks.
And let's look at the proof. On this huge benchmark test called MMLU, you can think of it like a final exam covering 57 different subjects. Chinchilla scored a 67.5%. That's a full 7 percentage points higher than the much, much larger Gopher, which in the world of AI is a massive leap forward. And hey, it wasn't a fluke. On another incredibly complex set of tasks called Big Bench, Chinchilla showed a very similar advantage. This proved that this new, balanced recipe consistently produces a smarter, more capable AI. So, this discovery, it effectively tore up the old playbook and wrote a new rulebook for AI development. It really changes everything about how we should think about building the next generation of AI.
So why does this all matter so much? Well, first, it means we can get way better AI for the exact same cost. Second, because these optimal models are actually smaller, they're cheaper to run and easier for other researchers to fine-tune and build on top of. That makes powerful AI way more accessible. And finally, it proves that the race for AI supremacy isn't just about who can build the biggest digital brain. It's just as much, if not more, about who can find and curate the best data.
And that leaves us with a really fascinating final thought. For years, the AI race was just a brute force sprint to build the biggest model possible. The Chinchilla scaling laws have fundamentally changed the rules of that game. So what happens now, when the race is no longer about building the biggest brain, but about competing to provide the very best education?